Alright, hey guys, y'all welcome to a brand new unit, Unit 12 on acids and bases. And so for most of you guys, kind of acids and bases are familiar, either just kind of from everyday life, or maybe you've talked about them in another science course before. But there's kind of one example that I normally like to start off by showing you guys, and that's a Coke can that has been placed in some acid. And I actually have one of these in the classroom. But what's interesting is after you take a soda can and put it in some really strong hydrochloric acid, it kind of reveals what the soda can is made of on the inside. And so believe it or not, what's actually on the inside of your soda can is a thin layer of plastic. You may be thinking, what? Really? But yeah, for real. And so let's think about this, kind of why do we need that thin layer of plastic on the inside? So when I placed the Coke can in the hydrochloric acid, only the aluminum dissolved while the plastic remained unharmed. So the plastic must be pretty acid tolerant. And so what happens is the Coke has acid in it. It's actually, pretty acidic. That's why, you sometimes get talked to about how it can, erode your teeth or, be used for kind of different stuff as well. And so that plastic, because it can withstand kind of the acidic effects, is used to actually protect the outer aluminum shell from the acidic Coke kind of within. It works the same way for kind of your other sodas as well, like your sun drops, kind of different things like that. And so it's just really interesting that the acidic or basic properties of something kind of affects how different elements are designed to contain them. And it affects just a lot of, how we go about kind of our daily life. So I think that's just kind of interesting to get you thinking about, the role of acids and bases. And so the first thing we're going to talk about is what are acids and bases like on the macroscopic level. And this is that idea of it's the level that is big enough for us to see, for us to feel, for us to, really observe on a larger level. So acids, they tend to, when you get them on your skin, they tend to sting. For example, ants, if you've ever gotten bitten by a fire ant, those release formic acid, so it definitely stings and hurts. And acids also tend to taste sour, like a lot of your citrus fruits, like lemons, limes, oranges. So a lot of fruits will have citric acid in them. Apple juice has malic acid. So it just kind of, gives that sour sort of taste that we associate with fruits. Now bases, on the other hand, tend to feel a little more slippery, so like soaps, laundry detergent, bleach, things like that. And they also taste bitter, so like if any soap has ever accidentally gotten in your mouth, that's not a really pleasant taste. And so just kind of throw this out there. Typically, if you put an acid together with a base, you have a process occur that's called neutralization. And so you can also often use this to your advantage. For example, if you get an ant bite and it is stinging, oftentimes you may put something like Benadryl cream on it. And so you may predict, that Benadryl cream must have, something with basic characteristics to kind of, help with that stinging a little bit. All right. But now let's kind of go on to the smaller level and talk about some sub-microscopic characteristics. So these are characteristics of acids and bases on kind of the tiny molecular level. And so acids, as you already know from the nomenclature unit, they contain hydrogen. And typically when you're writing that formula, the hydrogen comes at the front of the molecule. And so what happens is when you drop your acid in water, let's pretend that you've got your hydrogen and your chlorine. Let's pretend it's hydrochloric acid. What happens is those ions will break apart and you're going to produce hydrogen ions. And so that's one thing that's characteristic of an acid is it produces hydrogen ions when released in water. Okay. Now, another way to represent this hydrogen ion is by calling it H3O+. And the name of that is a hydronium ion. And the reason it's often written as that is because when you have those hydrogen ions floating around in water, water will often bind to them with one of those lone pairs. And so what that generates is a structure that has 3 hydrogens surrounding that one oxygen, and that structure has an overall positive charge. And so hydrogen ions, again, typically go on to make hydronium ions in water. Bases, on the other hand, they produce OH, which are also known as hydroxide ions when they are released in water. So for example, a common base is sodium hydroxide. And so when they split apart into water, you have your sodium ion, but you also have your hydroxide ion. And so that's kind of a key characteristic of bases, is that when dissolved in water, they produce OH hydroxide ions. Now what's neat is that acids, kind of when they interact with bases, they tend to donate their H plus ions, while bases tend to accept the H plus hydrogen ions from acids. And so if an acid is bringing the hydrogen ion to the table and the base is bringing the hydroxide ion, the acid will donate its hydrogen ion to the base, which will accept it. And what's neat is when you put H and OH together, you get HOH, which is the same thing as H2O. And so that's why acid and base reactions typically result in neutralization, is because you're forming water. So kind of cool. And just in that process, kind of what happens for that donation and acceptance to occur is the acid is kind of accepting a lone pair of electrons from the base, and the base is donating it to kind of claim that acid. That's a little more Chem 2 stuff, so if you decide to take that, we'll get into that more there. All right, so now, kind of with that in mind, let's stop for a minute and talk a little bit about what makes an acid strong. So we're looking at acid strength, and it has to do with a kind of a two-word phrase, and that is percent dissociation. And so if you are associated with someone, that means you are connected with them. You have things in common, you're maybe close together. And so what dissociation is the opposite. It's where you're breaking apart or unassociating kind of with each other. And so what makes a strong acid is where you have almost complete dissociation. So like at least 90% of the acid will break apart into hydrogen and the other ions. So in this picture here, the acid, before it's placed in the water, is a molecule where the H is connected to the negative ion. But then once it's placed in the water for a strong acid, almost all of those ions break apart. And so all the hydrogens are separate now. Okay, and that's kind of characteristic of an acid like hydrochloric acid. It's really strong, all those hydrogens break off. Now on a weak acid, you have much less dissociation, so like 20% or less, okay? And so what you'll notice is that a lot of the molecules have stayed connected even though they're in water, while only some of them have disassociated or broken apart from their negative ions, okay? And so what's interesting is take something like, vinegar, for example. It's considered a much weaker acid because it tends to dissociate at a much lower percentage. And the same analogy works for the strength of bases as well. Just instead of breaking apart to produce hydrogen ions, you're breaking apart to produce OH hydroxide ions. Now, right quick, what's really interesting about water is that it can act as both an acid and a base at the same time. And so the term we use for that is what's called an amphoteric substance. For example, you may have heard of someone being ambidextrous, which is where they can use their right and left hand kind of interchangeably. And so when you take two water molecules together, if you'll kind of watch this one on the left here, he's going to be accepting a proton, all right? So he's acting as a base, accepting a proton, and then the water molecule on the right is acting as an acid and donating his proton to the other water molecule. And so what that creates when that transfer has occurred is you get an OH hydroxide ion and an H3O plus hydronium ion. So there's your acidic part and there's your basic part. And so that's why water is considered to be neutral, because you typically find these acidic and basic pieces in equal concentrations when you just have pure water. And so just kind of neat, how it can do both. All right. So let's go to our next slide here. All right. So the way we measure kind of the concentration of the acidic hydrogen ions is using something called pH. And you're probably familiar with the pH scale, which for our purposes is going to run from 0 on the left to 14 on the right. If you go on and take more chemistry in college, you may actually encounter some acids that have negative pHs. Kind of crazy, but they are out there. And so for us though, 7 is going to be right in the middle, and so that will be neutral. Kind of from 0 up until that point, the lower side of the scale will be our acids. And then the higher side of the scale up until 14 will be the alkaline or the basic side, okay? So things with a high pH are basic, things with a low pH are acidic, things with a pH of 7 are neutral. All right, so one thing that we normally do in the lab for this unit is we get out a bunch of different household substances and let you test them with some pH strips. And so just throwing this out there, kind of because it's interesting to see what some of the items around us, how they rank on the pH scale. And so, for example, a lot of your cleaners and things are more basic, like you've got soap, your oven cleaner, bleach, baking soda even. One thing I found interesting is that eggs tend to be slightly basic. So I thought that was interesting. I didn't necessarily expect that. On the acidic side, you have definitely our fruits like we talked about, vinegar, tomatoes, bananas. But surprisingly, I also found that potatoes were kind of slightly acidic. And then of course we have water kind of right in the middle at 7. So anyway, it's just interesting to kind of think about the things around us. All right. So now let's talk about how pH is actually calculated. So pH, what that little p stands for, is actually the negative log of something, okay? And so the reason that we're going to use a log scale is these hydrogen ions are so tiny, all right? And so we need some sort of scale that allows us to talk about a lot of hydrogen ions using smaller numbers. So the log is kind of based off of a base of 10. And so that's going to help us when dealing with lots of these little hydrogen ions. Now we're also going to put it, well, what the negative does rather, is that kind of inverts or flips the log scale. And so the way that works is the more hydrogen ions you have, the lower the pH is. The less hydrogen ions you have, the higher the pH is. So it's kind of inverse of what we might think. All right, so what we're going to do is we're just going to write our formula and practice plugging in. So pH is equal to the negative log of the hydrogen ion concentration. You may sometimes see it written as pH is equal to negative log of your hydronium, but again, these are the exact same things. And so make sure on your notes that you have this formula copied down, because you'll definitely need it for the homework. So they tell us that our hydrogen ion concentration is 1.2 times 10 to the negative third. So we'll go ahead and rewrite our formula and include that in it. So we have pH is equal to negative log of 1.2 times 10 to the negative third. And again, it's measured in molarity because we're talking about concentration. So you'll get out your calculator and you'll hit the negative sign, then the log button. Then be careful when you're doing your scientific notation. Either use your E key or your times 10 to the key. And so it'll be negative log of 1.2 times 10 to the negative third. And then our pH comes out to be 2.92. So that means that the substance is acidic. Now, we don't normally worry about sig figs too much on these problems, but for those who are kind of interested in how they work, because this is a log scale, the way you know where to round off is the number of significant figures in your concentration should be equal to the number of decimal places in the pH. So for example, because there are 2 significant figures in 1.2, my pH should have 2 numbers following the decimal place. So the number of sig figs in the concentration tells you the number of decimal places in the pH. All right, so one more slide here. So what's neat is that there's actually another form of kind of the pH where we can do the opposite and measure the pOH. So instead of measuring the acidic hydrogen ions, we can measure the basic hydroxide ions. And the formula takes the same form, just instead of hydrogen ions, you're measuring hydroxide ions. Okay, but since the pH scale is equal to a total of 14, there's kind of a neat relationship between the pH and the pOH. So if you take the pH, kind of the acidic portion, and combine it with the pOH, the basic portion, they should add up to a total of 14, which accounts for your entire pH scale. And so what that means is that if you know either the pH or the pOH, you can calculate the other one easily by just subtracting. So they tell us that the pOH is 4.56, so we'll subtract that number from 14, okay? It cancels out on the right, and so 14 minus 4.56 is 9.44. And so again, the pH scale is what tells us if it's acidic or basic. So since this is a high pH, this means that it is something with a basic characteristic. All right. Well, guys, thanks so much. Again, this is a brief intro to kind of acids and bases. There's definitely a lot more out there, but this will at least get us started and get you familiar with a few more things. So thanks so much, and you'll have a great day.